Stop what you're doing. Seriously, stop revising generic definitions right now. If you're just sitting there memorizing textbook glossary terms for your Cambridge IGCSE 0478 exam, you are actively wasting your time. Worse, you're literally risking your grade boundaries. So let's just dive right into this explainer, because today we are going to completely shatter the illusion that those generic study methods actually work when the examiner puts a highly specific scenario right in front of you.
So let me ask you a question. Be honest, is this your go-to exam answer? Networks connect computers to share data using the internet. I mean, it sounds correct, right? It feels like you've stated a solid fact. You might even walk out of that exam hall feeling pretty confident that you absolutely nailed the question.
Well, here is the painful reality. That answer, it scores exactly 0 marks. Literally 0. And you might be wondering why? Because it is just way too generic. See, Cambridge examiners don't just want to know if you can regurgitate a fact you memorized. They want to see if you can apply scientific reasoning to a very specific scenario. If you don't use the exact scenario nouns given to you in the prompt, your answer is essentially invisible to the mark scheme. Context is absolutely everything here.
All right, let's jump right into Section 1, Network Fundamentals Unlocked. To actually get you scoring in that top band, we kind of need to completely rebuild how you look at networks. We're going to go on a quick micro to macro journey to see how networks function under the hood. I mean, our network evolution has been incredibly fast. Back in the late 1960s, we had ARPANET, funded by the US Department of Defense, and it was basically created just to share info between these massive, immovable computers. Fast forward through the 90s, where local organizations started connecting their employees' devices, and today, we have the modern internet, a massive, sprawling network of networks connecting billions of devices globally. But hey, it's not magic, right? It's physics, it's protocols. At its core, data communications really just rely on two main things, the transmission mode and the medium. You can send data in simplex, which is just one direction only. You can use half duplex, which goes both ways, but they have to take turns. Or full duplex, which goes both ways simultaneously. And that data? Well, it has to travel over something. It either uses wired mediums, like physical copper or fiber optic cables, or wireless mediums, which use radio waves or microwaves. You absolutely have to know exactly how your data is moving and what it's moving through.
And that actually leads us directly into network architecture. On one side of the coin, we have point-to-point networks. Think of these as dedicated, highly secure pipes between very specific endpoints. They have super low latency, great for reliability for sure, but honestly terrible for scaling up to massive systems. On the flip side, we have broadcast networks. These just blast information out to all connected devices simultaneously. Super simple to implement, but, and this is a huge but, they are incredibly prone to network congestion and something called broadcast storms, which is exactly why we rely on switches and routers to segment all that traffic.
Moving on to Section 2, Traffic Monitoring Systems.
So let's take all of this theory and apply it to a massive macro-level scenario pulled straight from your syllabus, urban traffic monitoring systems. Picture this, thousands of traffic cameras and sensors scattered across a super busy city, all of them transmitting data at the exact same time. How on earth do cities securely manage all this municipal data over the public internet? Well, they use a virtual private network, or a VPN. This lets the city completely separate its traffic camera data from your everyday public internet traffic by basically tunneling data link layer protocols right through the larger network. Now, I'm opening a little loop for you here. In just a minute, I'm going to reveal a hidden examiner clue about stateless protocols that will completely change how you answer this scenario for full marks. But first, you really have to grasp the sheer physical challenge of a system like this. Just think about the mobile communications required to pull this off. Data is constantly on the move. The single greatest challenge in urban mobile communications is successfully handing off that communication from one local coverage area to the next, across a whole succession of terrestrial wireless LANs, or WLANs. If that handoff drops, the entire traffic monitoring system fails. Ensuring that continuous coverage is an absolute nightmare to maintain if you're using heavy, connection-oriented protocols.
Which brings us nicely to Section 3, the UDP advantage.
This is the exact solution, and it closes that curiosity loop I mentioned earlier. To handle this massive influx of real-time data across hundreds of WLANs without the whole thing crashing, the system requires a very, very specific protocol. Enter the User Datagram Protocol, or UDP. Now, the absolutely most crucial word for you to remember here is stateless. All that means is it treats every single request for information as a completely independent transaction. It doesn't sit there wasting memory or time assigning storage space for conversations that are in progress.
It just fires off the data and moves on immediately. So, why does UDP absolutely win the day for traffic systems? Because it ruthlessly sacrifices error checking for raw, unadulterated speed. There is literally zero delay caused by error checking. For time-sensitive applications, we're talking streaming media, voice over IP, or real-time traffic cameras, this is just perfect. The server can handle a massive volume of these small requests incredibly fast simply because it isn't bothering to set up connections beforehand. And guys, this is the exact technical justification your examiner is hunting for.
Let's move into Section 4, Top Band Exam Strategy.
All right, now that you have the technical knowledge locked down, the evolution, the mediums, the architectures, VPN tunneling, and the sheer magic of stateless UDP, let's bridge the gap. We're going to transition this knowledge directly into the structural framework you need to absolutely ace that Cambridge exam. If you want top marks, you need this 4-step framework for every single scenario-based question. Step 1. Identify the concept. Step 2, extract evidence or data directly from the scenario. Step 3, apply scientific reasoning to connect the two together. And finally, Step 4, lock it in with precise examiner wording. If you follow this exact structure, you guarantee yourself maximum marks because you are handing the examiner exactly what their mark scheme demands.
All right, Section 5, Pause and Solve Challenge. Okay, let's actually put this to the test. I'm escalating the stakes a bit here. We're going to look at a highly realistic exam trap, and I want you to actively apply the framework we just talked about. Listen to this flawed student answer. Traffic cameras use a fast broadcast network so cars don't crash, sending data over the internet. Once again, it feels kind of related to the topic, right? But structurally, it is a complete disaster. It misidentifies the network type, it uses incredibly vague reasoning, and it completely lacks any real technical depth.
So, the big question, how do we upgrade this? I want you to literally pause this explainer right now. Seriously, take a moment, run through the 4-step framework in your head. Think about the difference between normal, everyday data and the extreme, high-volume data of a city traffic system. How would you rewrite this answer using UDP? Pause it, predict your answer, and then we'll keep going. Okay, ready? Here is your top bands upgrade. You start with the concept. State that the system utilizes the User Datagram Protocol, or UDP. Next up, the scenario evidence. You specifically mention this is essential for the massive data loads in urban traffic monitoring. Then comes your scientific reasoning. You explain that because UDP is stateless and completely eliminates the delay caused by error checking. Finally, hit them with that precise examiner wording. Wrap it all up by stating this ensures the low latency transmission that is critical for real-time video. Boom, full marks. Every single available point effortlessly captured.
Now, before we look at what's missing from your exam toolkit, I have a quick message to read directly from our syllabus guides. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations.
All right, let's be totally honest with each other about where you stand right now. Here's what you've conquered today. You understand network topologies, you get the absolute necessity of VPN tunneling from municipal data, and you know exactly how UDP's stateless speed handles heavy traffic scenarios for Paper 1. That's huge. But here is the gaping hole in your knowledge that this explainer deliberately left unresolved. All of this theory, it means absolutely nothing if you can't handle the linked practical data analysis skills and algorithms required for Paper 2. You know exactly how the data moves, but you don't yet know how to process it for the exam. That missing puzzle piece, the exact pseudocode and data validation techniques you need to not fail Paper 2, is waiting for you right now. What you need to revise instead is covered in the next explainer. Make clicking over there your mandatory survival step for these exams. Because at the end of the day, you have to ask yourself, are you ready to truly master the machine, or are you just going to memorize its manual? See you in the next explainer.